Good afternoon to all my students. So today in this lecture we are going to study some more important numericals of Z transform which are important as far as the exam is concerned. Okay. Yesterday we have seen in the last lecture we have seen a total number of 7 problems with region of convergence plotting. Okay. Today we are going to see few 3 to 4 problems and then we are going to discuss the concept of properties of Z transform which are very important. So first of all we will see some variety of numericals. So eighth problem. Okay, in the last lecture we have ended up to 7 problems. Today we are going to start with the problem number 8. So this is the problem: x of n equals to minus u of minus n minus 1 plus 1 upon 2 to the power n u of n. We can see that this is a both sided sequence. Okay, a two-sided sequence. So it has a negative side, also it has a positive side. Okay, so now we are going to see how we can plot, how we can solve these kind of signals and plot the region of convergence of this signal. Okay, so first of all write down the formula for Z transform. This is the formula for Z transform. In the next step we have to input the values. I'll zoom it. In the next step we have to input the values of x of n. Okay, just write down as it is. This is your x of n and z to the power minus n as it is. So now we know u of n. Okay, it's a positive sequence starting from 0 ending to infinity. Okay, and value is 1 for each sample. Less than 0 value is 0, greater than 1 value is 1, and this is we need to find out this u of minus n minus 1. Okay, there is a time shift of 1 in the negative cycle. Okay, so this is the figure for u of minus n minus 1. Already we have seen this kind of example in the last lecture. Okay, this is the sequence we are going to draw u of minus n minus 1 as it is, as like this. So now, as traditional format, the limits will change because there is a presence of u of n. So limit for summation for this one changes to n equals to minus infinity to minus 1. Okay, because it will start from this sequence starts from minus infinity and end to minus 1. Okay, and for u of n, for this term u of n, it will change from 0 to infinity. We already know this. So next step will be as it is. So no need to write this term because it is 1. This is u of n is also 1. So take the minus outside. Okay, minus have taken outside. Summation of n equals to minus infinity to plus minus 1 z to the power minus n as it is. Then second summation, n equals to 0 to infinity 1 upon 2 to the power n z to the power minus n. So next step, in the next step what will happen, we can exchange the limits. Okay, this n can be changed by this. So in the next step we can see minus outside as it is. So n lower limit will become minus 1, upper limit will become minus infinity without changing the sign because this is a property of summation. Then z to the power minus n as it is plus summation of n equals to 0 to infinity as it is. Then we can see here there is a common power. Okay, if we take z inverse instead of z, then the power will become common, which is n. So 1 upon 2 multiplied by z inverse. Okay, so after taking this as z inverse, the power will become plus n. So both the power will become common. We can take common power n. Okay, also I have written here limits changed without change in sign in order to obtain the fundamental term. Okay, so we are doing this kind of modification or alterations because we need to convert our equation into this format to find a suitable solution. Okay, so here is, but it's not in the fundamental term because here it is minus n. This term is available in this format, but this term z to the power minus n, we need to alter it again. We need to modify in order to obtain in this term. So for that we have already done this kind of examples. Okay, we need to put n equals to minus n, because when we put n equals to minus n, this will become plus n. Okay, so minus outside as it is, then n equals to minus n means this n will become plus, this will become plus 1, this will become plus infinity. So n will be 1 to infinity z, and this minus n will become plus n as it is, plus summation of n equals to 0 to infinity as it is. This term is as it is. Okay, no need to change. So now again we are not getting this fundamental term. Okay, the condition is lower limit should be 0, upper limit is infinity. We are getting upper limit as infinity, but lower limit is 1, so we need to convert it. Okay, so for that we have to put n minus 1. Okay, this term will become n minus 1 equal to 0, so n minus 1 will be m, so it will be m equals to 0, then n equals to m plus 1. Okay, we have done this kind of also problem in the previous lectures. Okay, so x of z equals to minus outside as it is, summation of this will become m equals to 0, this will remain in infinity as it is, then z, this n will become m plus 1. So write down z to the power m plus 1 plus summation of n equals to 0 to infinity and this term as it is. Okay, now we need to split this term z. Okay, firstly multiply the power with z by, so for it will become z to the power m into z power 1. Okay, this term as it is. So we need to take this z outside because it is not associated with m. So you can see that this summation consists of m terms. So this summation will take the summation of this term only, this it will not take summation of this. Okay, so need to take it outside, so z taken outside. Okay, I've written here, then summation of m equals to 0 to infinity as it is, z to the power m remaining, plus this term remains as it is. So now this is the point at which we are going to find out our region of convergence. Okay, so this will become r1. Okay, this term for region of convergence criteria, this z should be less than 1, mod of z should be less than 1, and for other 1 upon 2 mod of half into z to the power minus n should be less than 1. So call it as r1 means roc1, this one is roc2. Okay, we have to take the intersection. So for this we can see that there is only z, so mod of z less than 1. Okay, this is roc number 1. We have to simplify this equation. Okay, so we have taken this equation as it is, so mod of this equation less than 1. So again 1 upon 2 as it is, z inverse can be written as 1 upon z, so mod of this term less than 1. So now when we cross multiply z with 1, it will become mod of z. Okay, and 1 upon 2 remains as it is. So this equation indicates that mod of z is greater than 1 upon 2. This is your ROC 2, R2. So now in order to find out the region of convergence, we have to take the intersection of both the ROCs, intersection of R1 with respect to R2. So here we can see that there is only one greater sign, okay, in this R2. In case of R1 there is less than sign. So intersection is taken only when there are two greater than signs. Okay, so if there is a less than sign, then the ROC will be in between the 2 points. So in this case the ROC will be in between half and less than 1, okay, or 1. So this is the ROC. So we have to solve this. Okay, we have find out the ROC, but we need to solve this equation for a perfect solution. Okay, so now we know that this is a fundamental term. Okay, 1 upon 1 minus alpha. This is alpha, this term is alpha, and this term is alpha. Just write down 1 upon 1 minus alpha. So minus z upon 1 minus z. Minus z is this one, okay, outside. Okay, and 1 upon z means 1 upon a, 1 minus a, and plus 1 upon 1 minus half z inverse. So this is a. This is the solution. You can also simplify it. Okay, for example, this is simplified as 1 upon 1 minus z inverse. Okay, plus this is as it is. So the ROC is the intersection of R1 and R2. Okay, so it will in between half and 1. So ROC is in between half and 1 because in both the ROCs there is a less than and greater one. We cannot intersect R1 and R2. So ROC is plotted between 1 half and 1. So this is the plot of ROC. Okay, image real. This is real part. This is imaginary part. This is imaginary part. So now we need to draw two poles. Okay, this is half and 1. Half can be written here, 1 can be drawn here. Okay, and as I said, ROC is in between the two concentric circles. So draw the circles and draw the ROC in between the two circles. So for both sided signal, so for the signal consisting of positive and negative sequences, ROC is in between the two concentric circles. This one and this half. These are two concentric circles, and ROC is in between the two concentric circles. Okay, this is the solution for the example. It's a different kind of example. Okay, so now next one is also a different kind of example. In this example, they have given the intervals for x of n. So first interval is 0 for n less than 0. Second interval is 1 for n greater than 0 and less than 9. And third one is 0 for n greater than 9. So this indicates that our signal will be from 0 to 9. After 9 it will be 0. Before 0 it will be 0. I have drawn here. This is the signal. Okay, so it will be 1 for 0 to 9. Otherwise it will be 0. So first step we have to write down the Z transform formula. Okay, then we have to put the values of our summation and x of n. So now x of n is 1 because for other signal it is 0, and summation limit is our signal starts from 0 ends to 9. So summation limit is from 0 to 9 and z to the power minus n as it is. So now z inverse to the power n. Okay, because our fundamental equation is like that only. For that purpose we have to take z as z inverse and n power. Okay, but for the fundamental equation the summation is n equals to 0 to infinity, but here the upper limit is 9, so there is a different formula for this kind of summation. So for this kind of summation the formula is given as n equals to 0 to capital N. Okay, this is 0, this is capital N, some finite value. As we know that this sequence is a finite sequence. Okay, so it has finite value, it will not get infinity. Alpha to the power n, this is alpha, this is power n. The solution is 1 minus alpha power n plus 1 upon 1 minus alpha. Just write down the value of n and alpha in the next step. So 1 minus value of alpha is z inverse, value of n plus 1 is 9 plus 1 equals to 10. Again in denominator 1 minus alpha is z inverse. So as we know that this is a finite sequence, so the z plane is the entire ROC. Okay, so for finite sequences the ROC is the entire z plane. You can see this is the diagram for ROC. So ROC is entire z plane. Okay, this was a simple problem. So now we will going to see an important problem which consists of sine. Okay, so x of n equals to 1 upon 3 to the power n sine of pi by 4 n u of n. Basically it's a positive sequence. Okay, right-handed sequence, but we have to simplify this term. Okay, let's see how it is simplified. First step, we have to write down the formula of x of z means z transform. In the second step we have to check the limits of the summation. So here it is u of n. So now we are going to put the limit of summation from 0 to infinity. Okay, lower limit is 0, upper limit is infinity because of u of n is present, and then u of n is equal to 1. Okay, next step you have to write down x of n. So write down x of n, this is x of n, write down x of n here as it is with z to the power minus n. So now there is a term. Okay, so sine of pi by 4 n, it has a value, so its value is given here. Sine pi by 4 n can be directly written as e to the power j pi by 4 n minus e to the power minus j pi by 4 n upon 2j. It's basically a polar form. So I've written here 1 upon 3 to the power n as it is. Sine pi by 4 value is written here, which is this value, and z to the power minus n as it is. So now we have to simplify. Okay, so just take 1 upon 2j outside. We can see here this is n, this is minus n. Okay, this can be multiplied, okay, by taking common n, but 1 upon 2j can be taken outside. So take 1 upon 2j outside, then summation of n equals to 0 to infinity. Okay, as it is, this term is multiplied with this term, this only, because it has power, common power n. So 1 upon 3 into e to the power j pi by 4 n and z inverse n. Okay, so here z inverse is taken, so we will get power of this z as positive n. Okay, again minus, here minus 1 upon 2j outside, summation of this term into this term and this term. Okay, this term. So summation of n equals to 0 to infinity 1 upon 3 into 1 upon 3 into this term this one, it will become e to the power minus j pi by 4 n, and z inverse taken, so that we will get power as small n. So now this is the point at which we are going to find out our ROC. So consider this as ROC number 1, this is as ROC number 1, and this as ROC number 2. Again we have to take the intersection. Okay, so we will solve step by step. So R1 we will solve for this one. So mod of this whole term should be less than 1. I have written here mod of 1 upon 3 into e to the power j pi by 4 into z inverse less than 1. Okay, now simplify. We know that we have to find out the value of this term. Okay, this term has a value. The value of this term is e to the power j pi by 4 equals to cos of pi by 4 plus j sine pi by 4. Okay, this is a predefined value. So now mod of this value will be square root of this. Okay, so square root of cos square pi by 4, j will become minus 1. Okay, sine square pi by 4, this will be 1. Okay, so value of this is 1, so no need to write any value for this. Okay, as it is 1, so 1 upon 3 and z inverse remains. So mod of 1 upon 3 z inverse less than 1, so we can write z inverse as 1 upon z here, less than 1. So now after cross multiplying this z with this 1, we are getting mod of z greater than 1 by 3. So this is our R1, mod of z is greater than 1 upon 3. So in the second, to solve the second ROC, we need to write this equation, mod of this equation less than 1. Again we have to find out this term. This term is similar to this one, it has value 1. Okay, no need to solve. So mod of this term is 1, so only 1 upon 3 and z inverse remains. So mod of 1 upon 3 and z inverse less than 1, so z inverse can be written as 1 upon z, so this will become similar. So z greater than 1 upon 3, and R2 is also z mod of z greater than 1 upon 3. Okay, this is the both ROCs. So before plotting the ROCs, we need to find out the solution for this equation. Okay, so now we can see here, this is our alpha, this is our alpha. Just write down 1 upon 1 minus alpha. Okay, in the solution 1 upon 2j outside, 1 upon 1 minus a. So we can write here 1 upon 2j outside, so 1 upon 1 minus, this is a. In the second, minus 1 upon 2j outside, so 1 upon 1 minus, this is a. Okay, simple. So this is the solution. So now ROC for both the sequence is common, so we need to take only one ROC, which is z mod of z greater than 1 upon 3. So this is a, as already I have said before solving the problem, this is a right-handed sequence. So the z plane, sorry, the ROC will be outside the z plane. Okay, so because of mod of z greater than 1 upon 3, this is our outermost pole 1 upon 3, so ROC will be present outside the outermost pole 1 upon 3, it will not present inside the pole. Okay, outside the pole 1 upon 3. This is the solution and ROC. So now example number 10, I will give you this example as a homework. Okay, you can solve it, it is very simple example. What they have given x of n equals to a to the power mod of n. Okay, and they have given mod of a less than 1. So just I'll tell you the trick for that. So this is mod of n. We don't know if it is a positive or negative value, so we have to denote that x of n is, first put negative value here. So x of n equals to a to the power minus n for n greater than, for n less than 0. If n is less than 0, this will become minus n. If n is greater than or equal to 0, this will become plus n. Okay, these are the two conditions. Okay, this is the plot. So from this, or from this, we can say that it is a two-sided sequence, positive as well as negative sided sequence. Okay, so already we have solved this problem. So for a two-sided sequence, the ROC is in between the two concentric circles. Okay, so simple example I have written here, the tricks or the steps. Okay, so first of all we have to split x of n from minus infinity to 1 minus 1. Okay, minus infinity to minus 1, and then 0 to infinity, 0 to infinity. Okay, and then we have to solve. Okay, this is a simple problem, we can solve it very easy. Okay, and this is the condition to find out the ROC. Okay, so mod of this should be less than 1 and mod of this should be less than 1, less than 1, less than 1. So this will become z less than 1 upon a, z greater than 1 upon a. So ROC is in between 1 upon a and a. So which term will be near to 0? Okay, suppose if we will put, I have given here, so ROC is this, mod of z greater than a and less than 1 upon a. Okay, so I have given here, if a is less than 1, then a equals to 0. Okay, it will really less than 1. If 1 upon a, sorry, if a is less than 1, so in the second case, in this case it will 1 upon 0.5. For example, we have taken 0.5, so 1 upon 0.5 will be 1, or 0.6 we have taken, 1 upon 0.6 will be 1.2, so it will be greater than 1. Okay, so we have to take this a, this one near to 0, this pole near to 0, and this pole after this one. So first one is a and second one I have taken 1 upon a, and the ROC is in between the two concentric circles. Okay, because mod of a less than 1. Why I have taken less than 1 for this? Because in the question itself they have given mod of a should be less than 1, value of a should be less than 1. Okay, you can solve it. If there is any problem, feel free to contact. Okay, so now we are going to study the properties of Z transform, the important term. Okay, the first, we have already seen the properties of continuous time Fourier transform, then discrete time Fourier transform, and now we are going to see properties of Z transform. These are quite similar, there is no difference. Okay, just the difference is Z. Okay, in case of continuous discrete type Fourier transform, it is e to the power j omega. Here it is z or n. So first property is linearity. Okay, this property is nothing but superposition theorem or homogeneous theorem, where weighted sum of two sequence is equal to the output of weighted sum of two sequence. So this property states that Z transform of x of n is x of z with ROC R1. Okay, then also Z transform of this y of n is y of z. Okay, this is Z transform. So when we take Z transform of this, we get y of z with ROC R2. Then we can write as weighted sum means a into this x of n plus b into this y of n z transform. So when we take z transform of these terms, we get weighted sum a into z transform x of z plus b into y of z, and ROC is intersection of the two ROCs, R1 and R2. Okay, simple, no need for any proof. Second one is time shift property of Z transform. So if we are taking Z transform of x of n, we are getting x of z. Then if there is any time shift is minus n. Okay, you can see here x of n minus n0. Then Z transform is z to the power minus n naught, z to the power minus this time shift n naught into x of z. Okay, this is the property. Third one is scaling in z domain. Scaling is nothing but addition of a constant term with some power. So if we take z transform of x of n, it will be x of z. Then if there is an introduction of the term alpha to the power n into x of n, okay, there is nothing but introduction of this. If there is any kind of this term, you can write it as x of z upon a. Okay, so z transform of this term is x of z upon a. Okay, simple. So next is time reversal. Time reversal is nothing but change in the sign of x of n. So if this property states that if z transform of x of n is x of z with ROC r, then a time reverse in the x of n. Time reverse in x of n is nothing but x of minus n. So z transform of this time reverse is x of 1 upon z. That's it. With ROC 1 upon r. Okay. So next one is convolution property. Okay, we know that convolution is nothing but multiplication of two sequences. So if x of z transform of x of n is x of z and z transform of y of n is y of z, then we can write as convolution of these two, x of n convolution of y of n, z transform is x of z into y of z. So convolution, so the z transform of this convolution is x of z into y of z. Okay, and the last one is differentiation in z domain. Okay, so differentiation in z domain is nothing but multiplicative property, kind of. So I'll explain. If z transform of x of n is x of z, then this is a term, I'll zoom it, this is a term associated with x of n. Okay, constant term n. If this kind of sequence is there, so z transform of this sequence is minus z into derivative of this. So whenever there is a term multiplied with x of n, which is simple term n, then z transform of this term is minus z into derivative of this term x of z. Okay, so this is for today. So I think we have covered 70% of 5th chapter. Now in the next lecture we are going to study how to find out inverse z transform and the steps for inverse z transform. Okay, so I'll take the leave and this is for today. So see you in the next lecture, and do watch the videos with reference to the PDF. Okay, I have uploaded this PDF of this lecture in the Teams. Okay, so do watch, and if there is any problem, feel free to contact. Okay, uh, take care and stay safe, stay home. ठीक है, bye.